All right, so thanks for the introductions. Today we will just focus the topics of this webinar, linking the roughness quantifications together with the functionalities of the surface. So as you have noticed, to ensure that everyone has the best audio experience, everyone else is muted in a way that we can get a clean audio signals. In that case, feel free to really ask questions during the sessions by using the chat box and dropping your questions over there. As we'll know, at the end of the webinar, we will have a 15 minutes dedicated for the Q&A sessions, such as we can answer this question. And in case we cannot answer all the questions, we will later on by email make sure that we deliver the answer to you. Also, this webinar will be recorded and be available offline. So you will receive a link where you could just download further these presentations and distribute it to anyone who will be interested. So today, this webinar is very pragmatic and oriented to real cases. So the key learning point you will get from this webinar is, first of all, the best mean to measure roughness for your applications, because we have multiple instruments that can measure roughness. Of course, within this instruments, such as if we look for non-contact profilers or stylus profilers, we have a difference between measuring roughness as a profile or as an area. So we will elaborate on which cases or which application are best covered. Also, as we know, we have new areal roughness parameters brought by the norm ISO 25178 with the so-called S parameters. So we'll see and you will learn how well designed those S parameters are in order to really link functionality of the surface together with its roughness. Also, in a pragmatic way, whenever we discuss about roughness, there is a need to use a cutoff and make sure we define this cutoff according to the applications. So you will learn also how a methodology on how to select this cutoff. And last but not least, you will see a series of concrete examples where the most relevant parameters will be aligned versus and correlate versus functionalities. So prior to start, we are part of the Nano Surface divisions, and our core competencies lies on studying surfaces. So we can go all the way through non-contact 3D optical profilometry, such as white line interferometry and focus variations with Bruker Alicona. But also we have high-end stylus profilometry for step height, roughness measurements, as well as atomic force microscopy. But we are not limited to study the surface. We like to test them through mechanical testing, such as nano annotations or wear testers, for instance. So all that bring us ability and unique positions to bring some key applications and share that with all of you. So roughness is really a wide topic. Whenever we speak about roughness, we can speak about actually quantifying wears, because whenever a surface starts to wear out, like this sensor one, its roughness evolves. So quantifying roughness is equivalent of quantifying wear and be able to investigate the failure mode or to better design the surface for a longer lifetime. Texture also is another word where roughness can play a role. By texture, we express this idea that the surface texture is designed for a specific purposes, such as a more efficient and less consumptions, for instance, creating less noise or less shatter, or in a simple way look for shinier or made surfaces looking. So roughness is playing a key role to define textures. And last and not least is roughness help you to take your manufacturing process under control. So with roughness parameters, we can monitor the productions, check whether parts are compliant or within the tolerances, and in that way we have both entry control, where we will look and assess a supplier, or we go for output control, where we confirm that the part is within the customer specification. So roughness is really a big deal across industries. And nowadays, roughness also come up to a very wide range. So on the left side, you see different processes like CNC processes, as well as process and finishing processes, where we can see the roughness here, the mean roughness RA, ranging from anywhere from 50 microns till something below 0.01 microns, so 10 nanometers. So we see that the roughness is very widely spread across. And the most important is now it starts to go to a very large volume and demanding roughness. So if you look to aluminum or stainless steel laminations, all the roughness is below 0.1 microns to assess and ensure that the whole sheet will be useful for then a car, automotive application, or food. In the same way, everyone having a cell phone or display nowadays get a glass with a roughness around few nanometers. Same apply for high-end bearings, for instance, or optics. So in general, roughness can go to down smoother and smoother surfaces around 0.1 micron, and this is where we go to high-end application requiring key check and understanding in depth the surface structure. Also, roughness measurement has evolved. We started to measure roughness through stylus mechanical profilers, where a tip just scan across a surface. In that case, it's depends on how much application has evolved, because nowadays we have more complex engineering surfaces. So if we go to 3 specific examples, like a CNC turn surfaces, a texture surface from the own cylinder, or a more random surface, which could be from additive manufacturing or abrasive papers, we will have tendency to use different techniques. So for CNC processes, having a single line will definitively go across the surface and get a very fidelity reproductions of how the surface looks like. The areal measurements can also give to you this information, but there is no real need for areal measurements on that kind of a specific application. Whenever there is some kind of processes to really texture on a purpose a surface, such like the awning structure you can find on engine block, then it starts to be challenging to, with a single profile, to assess the reality of the structure, because if you scan in one line, maybe you may miss this specific values. So this is where the areal measurements will help and gain in terms of statistics, but also in terms of how representative the measurement is from what the surface is truly. The last type of surface is a random surface. So it can be anything regarding additive manufacturing, where we have partially melt particle, for instance. It can be abrasive, like here, where you have a flat surface and a pit point to scratch the surface. Then in that case, a single profile can see a very flat surface or can see a very rough surface. So in that case, single profile is not the solutions and will not be representative. In that case, areal measurements, so full field of view, will be mandatory. So depending on your application, you may want to range from anything like single profile or full areas, depending on how complex and how random the surface is. In terms of roughness measurements and in terms of norm, norms for single profile is there since a very long time, and it's defined by 4287 ISO norm, and everything is really defined. So it defines whether your profile is periodic or random, and then the cutoff are well defined together with the evaluation length. So you know exactly how long the profile should be and what kind of filter and color to apply. So in that sense, it's very well squared out. However, with the areal roughness parameters from ISO 25178, the cutoff is defined by user. So it brings a large freedom that help us really to define exactly the component of surface we're interested in. So you can go from raw surface, and then you get this surface after shape and form removal, and from there the norms allow you to extract whatever component you want. So you may extract a bit of waviness, or you may extract the roughness or the micro-roughness. You just need to specify the cutoff. And in that case, as you will see, what's become critical is to define the cutoff as per the applications, and to know exactly which component of the surface is responsible for the main functionalities. And in that case, everything we'll do will be encompassed within the ISO norm. However, roughness is very challenging and complex in a sense that you have pitfalls. And measuring a roughness is easy. Measuring a roughness which is representative to a surface and which can be linked to a process or to a certain efficiencies is far more complex than that. And the complexity comes to actually three main pitfalls. The first pitfall is actually to determine whether the roughness instrument we use to measure the texture has a proper lateral resolution. So what you see here is the true surface in purple. So if you use a sharp enough stylus, you would get some kind of a right assessment on how the surface look like. However, using a stylus which is far bigger will bring you a very different surfaces, and you will elude these valleys, for instance, that could play a significant role as a lubricant reservoir, for instance. However, lateral resolution is more complex than that, and usually this has to do with how the system is specified by the manufacturers. So here, for instance, if we take example of a non-contact optical profilers as a metrology system, we define ourselves the optical resolution, which is 3.8 microns. So this optical resolution is a physical limit on what this objective can achieve. So it tells you that this objective can measure up to, let's say, 4 micron spacing or line space by 4 microns or details of 4 microns. However, because we use digital cameras, we can, and zoom, we can end up with a pixel size around 7.2 microns. So here is really what the camera can see. And in that case, the limitation is not objective but the camera itself. So in that configuration, we will only see 7 microns. So any details of 4 microns will absolutely be smeared out and will not be shown. On contrary, we will need to use a higher zoom lens, such as we obtain a 2 microns pixel resolution. But again, here it doesn't tell you that you will have and resolve 2 microns details. You will still continue to resolve around 4 microns. So be careful and assess the lateral resolutions by a specific grading with a specific spacing, such as you can see whether we can indeed resolve a lateral structure. The second point is we have to assess the vertical resolution, simply because roughness relied on measuring the vertical fluctuation across a given plane or given line. In that case, we have to define capabilities of the system on the metrology level by measuring, let's say, a known step height and performing a repeatability test. So here this is an example of copper line measured 10 times, and you see this is a 9.5 micron thickness with a standard deviation of 1 sigma below 1 nanometer, so it's 0.7 nanometers. So it means that here the system has a capability to indeed measure in this given conditions around nanometer levels. So it's pretty easy and straightforward test to do, but it's revealed a lot in terms of vertical capabilities. And the last one is actually the combination of both. This is what we call transfer function, the most complex, because we are measuring x, y, z coordinates for the points on an areal measurements. The noise, the lateral noise and vertical noise are coupling together in a very strong manner. So in that case, you see the same surfaces measure with a capable system with low noise, and the same area measure with noise added on the vertical directions. And what you see here is definitively a very different surfaces. So that image is the right one and correspond to what the surface is. So it's really some kind of peaks that will sustain high pressure and get the grips. And this surface, if we don't pay attention, will look like more sustaining a large bearing load and made really to not really slide, why it's the same surface. So in that case, you can see how different the surface looks like after seeing it through the instrument. So that's very challenging, and this is where most of the issues correlating roughness parameters with efficiency comes from. If you have the right instruments, you can easily correlate. If the background noise is too high, unfortunately what you will assess is every time the system rather than the surface you want to discriminate. So now we have different techniques to measure roughness. Here at Bruker we have the complete portfolios in order to cover all the needs, and every allocation between system and capabilities are summarized into this graph. So we have the vertical height on the y-axis, we have the lateral resolution and extensions on the x-axis. Both of them are in a logarithm scale, so we are ranging from 0.1 nanometers till 100 millimeters, and from below 0.01 nanometer all the way to 10 millimeters. And what we see is AFM, which is atomic force microscopies, allows to profile, let's say, surfaces whenever you need high lateral resolution. And we will have a limitations on terms of measuring the Z range that will give to you that will be given by the Z range of the scanners. So whenever you have details below 0.5 microns, usually AFM will be the right techniques. If you start to have very small vertical steps or small roughnesses, but you want to extend to larger areas, the white line interferometry will play a role. And everything which require vertical precisions below 0.1 microns will lie on the coverage by white line interferometry techniques known as coherent scanning interferometry as well. By vertical precision, I mean that we can measure maybe 10 or 100 micron step, but still the precision at which we need to measure it will be well below 0.1 microns. So usually like MEMS devices will need to measure 10 microns at few nanometer levels. Everything above, going to larger field of views, rougher surfaces, texture surfaces, the focus variation technique will be way more efficient, having higher throughput, having ease of use. So by adding the two techniques, we nicely cover the full application range. As you can see, the stylus profilers of DECTAC can certainly cover most of the applications. But the main reason why it is still in use are twofold. The first one is we can easily break, let's say, the standard light diffraction limits of 0.5 microns by using sub-micron styli, such as 0.2 microns, and see details around 0.2 microns without switching to atomic force microscopy. And the second point is this technique has no issue with multi-thin transparent layers. So for thin film below 0.1 microns, it can be with metallic surfaces or transparent surfaces. Light will not be able to distinguish very well on optical profilers the interface. So the stylus profilers remain the right solutions. To further elaborate in terms of principle for the optical profilers, we all both use for focus variation or white line interferometry technique an objective which focuses a light over a given surface. And then we perform a vertical scan while capturing intensity images from cameras. The main difference is focus variation is using a bright field objective and look for adjacent pixel and look for the best contrast. The best contrast will become the focal plane, and every pixel will see these calculations in order to reconstruct a 3D map of Z height. Regarding white light, we use interferometric objective which project a moire, and this moire is very finely defined on vertical space, so around plus minus 0.5 micron. So whenever there is a progress, the system records the Z height for every pixel for which the moire is present. So pretty easy technique. However, the main difference is by using this moire, we gain extra capabilities. So for white light interferometry technique, we are fully independent from objective regarding vertical resolutions, and this have a clear impact on how we measure all the system. So for instance, we can use objective with pretty long working distance, which would mean on any other technique poor Z resolutions, but still keep the nanometer vertical resolution due to the presence of fringe. So here you see the objective being in focus of the bottom of the scope, measuring whitish peak materials, and still be able to measure here a complete waviness around 30 nanometers. The same apply with an objective and mirrors that deflect the light to horizontal way, such as we can measure vertical wall roughness, and in that case we see here on the crankshaft the shatter of the CNC tool that creates a roughness around 0.1 microns, and this is millimeters square which are measured in a single acquisition. So if there are, let's say, main points about this white line interferometry technique to use, it allows large field of view together with ultimate nanometer vertical resolution independent from objective. So we start to have something interesting for roughness. And indeed, this is what's happening with roughness. And this is where we want to come up with the point is whenever you want to correlate whatever roughness or micro roughness and correlate it versus its functionality or efficiency, we have to make sure that the system has a unique transfer function. And this is an example here of a grinded surface. You have two images taken, and the overall acquisition here took only 20 seconds because we were using a 5x objectives with a 3.6 micron lateral resolutions. And in that case, this complex surface can be actually decomposed into waviness. If we take all the long range wavelengths above 0.8 millimeters, you can work and separate really the roughness itself, sampling from 0.8 millimeter till 0.08 millimeters. In that case, you see the mean roughness goes down to 1 microns. And then you can go even further and try to sample the micro roughness. And basically here you see that immediately the mean roughness become below 0.3 microns. And this kind of decomposition can only happen with white line interferometry, especially the third step. All other optical technique will simply get this right, this one almost right but start to be noisier, and this one will be full of noise. And actually whenever you engineer surfaces, you never know which one of the components will play the significant role, and the difference between a good or bad surface may lie to that kind of regime. So it's very important to understand how far you can go with any roughness measurement system. Here, white line interferometry is really designed for sub-microns roughness measurements, even on a large, tall, high difference like this one, where we see a vertical range of 10 microns, but finally you get a true vertical resolutions of 1 nanometers. Once you have this, you can start to have a robust way of measuring roughness. But the key question is, why don't we stop with just getting mean roughness? Actually, mean roughness will not be helpful in most of the cases because it's a fairly stable but too stable values, and it does not discriminate different shape of surfaces. So you have that the profile drawn here, you have a certain higher frequencies or triangle or some kind of reversed triangle. All the surfaces get the same RA. On area level, the two surfaces here get exactly the same SA. So now you understand that this RA or SA only discriminate the amplitudes and does not play any role regarding the spacing between any peaks or valleys. Why? This spacing is very critical. So for instance, this type of surface is made to nicely bear pressure while having a reservoir for oils. This one is great to grip or grind or abrade surfaces, and this one might be a nice sliding one while having still enough reservoir for lubricant. So you can see that depending on application, most of the time the RA or SA will not be enough. And this is the whole point of this webinar, is now to present case studies where we understand what we need to do and which parameter to pull out in order to correlate. So the first way to ask is really how can we choose the cutoff. This is an example of the same location, same surface, of aluminum compound, which is under corrosion study. So there is like corrosive gas, and we like and see how much modifications happen on the surface to better estimate, let's say, the failure point. And in that case, we don't want to look to the surface, we just want to plot a single SA mean roughness, for instance. So the way to analyze the surface is we see visually that you have tiny higher structure that appear. So the corrosion, let's say, destruct the smooth surface and create tiny little defects. Well, this defect will be nicely spun out by what we call pore spectrum densities. And this is so-called Ph.D graph. And Ph.D is no more no less than plotting the roughness for a given spatial frequency. So we can see the roughness variations as per the spatial frequency, so as per the size of the details. And what we see here in terms of that part is really the more or less what we call waviness, and here will be more the roughness filtered. And what we see is the waviness here is fairly the same whatever the corrosion state, but after that you see after a certain special wavelengths around like 30 times per millimeter, we start to see differences. And what we can do is just record and ask for a certain cutoff and bandpass, such as we average out the mean roughness along that frame, and then we will integrate the difference such as we can get a nice term to track in terms of roughness. And this is usually the way we do. A practical example is the first case, which is like obtaining a mirror by depositions of aluminum coatings. And the coatings was, let's say, leaving either very shiny or relatively matte surfaces. And of course, as a mirror, you want it to be as shiny as possible. So if we look to analyze and measure the surface with single acquisitions, 5x objectives, and wide line interferometry, we will get a nice pore spectrum density along X and Y surfaces. And if we look around, we can see that there is some kind of differences on that regions and also on that specific regions. And this is where we'll see a difference there. So if we apply a bandpass to just select this special frequency, here what we obtain. So we obtain now a filtered surface, and what we see on matte appearance and shiny appearance, we already see visually a difference because this is the same z-scale. So you really see that on the matte you have some kind of micro roughness where you still have a very well aligned texture, and this texture will definitively diffuse light in a different angle, which will create some A's and get the impression of matte. But also if you measure and get and calculate the mean roughness SA, you see that actually we have half roughness in case of shiny appearance. So now you have directly a simple mean roughness parameters to quantify the appearance and the reflectivity efficiency of the mirrors, which is quite straightforward. And here the sole requirement was to select the right cutoff. To continue with more like optical surfaces, we can quantify with the kurtosis parameter how opaque a glass is. So glass window from windows, we want them to be either fully transparent, either to be slightly opaque, or just transmitting light but not transmitting details, such as you have a bit of privacy. In that case, the glass manufacturers are texturing surfaces in different ways. This texturing will help actually to create a certain effect. And the question is, how do we control in the process whether the process is deviating or not, and how do we rank the different opacity or impact of into the opacities? Well, kurtosis, its SKU helps. So the kurtosis simply quantify how the height distribution looks like. So either is equal to 3 and we have a nice Gaussian distribution, either is higher than 3 or lower than 3 to get this repartition. So what we see across these different surfaces is the kurtosis definitively varies a lot. So I on purpose put just the order in magnitudes because you see that some kind of standard rough side is around 40. If you start to really structure a surface with pits and with a certain waviness, you go to very high values. The mate is more around 1000, and the well structure is around 200. So in that way, you have a highly fluctuating parameters, which is linked to how the texture is. So it amplify, magnify, let's say, any surface entries. So it's a perfect parameters whenever we are in Industry 4.0 to feedback to the process manufacturing and see any little tiny deviation, such as process can be modified prior of having any issues. To continue with really light interactions, so we can use a parameter called skewness to quantify efficiency of solar cells. So the solar cells are from polysilicon surfaces, and skewness actually tells you how much the height distributions is skewed toward peaks or valleys. So a perfectly centered distribution will be 0 in that case. So if you look to the 3 different surfaces of this polysilicon surface, there is some kind of wet etching, chemical etching, that helps to create the structures. So there is a way for in the process we can control and get either this type of surfaces or this one. The point is, due to the variability of polysilicon and the variability of the wet bath, there is a need to control the final states and do a further etching or not. So in that case, if we look to the roughness, this surface is the highest efficiency, this one the lowest, and unfortunately the roughness of very low pore efficiency is almost the same as a medium, and only twice lower than the standard one. So if we look to the skewness will actually nicely correlate with efficiency almost in a linear way. And what we need is get around -1, so have enough depth such as we can nicely measure and make sure that the photons are well captured before to be transferred into electron. So in that case, again, a very simple skewness parameters will help to feedback the chemical etching process and define whether the conditions are right for the wet bath and how much further etching is required, no more, no less. Now we are coming down to the mechanical word. So mechanical word is, first of all, here a coupling between a cap and its ultrasound sensor. So the ultrasound sensor need to be encapsulated. However, encapsulations is critical for protections, but also this coupling between the sensor and the cap should be very well matched. Otherwise, the ultrasound sensor will lose all efficiency. So as you can see, we use super long working distance objectives, such as we can look to the bottom. No way for a standard objective to go in. And we can, with a single measurements, we can assess and measure the full bottom cavities. And in between the good and the bad, you see on the same z-scale that actually on the bad coupling cap, actually the bottom has been got an issue in terms of machining. So the CNC was vibrating, there were some shatters, or there was some issues in terms of the tooling that triggered this kind of surface fluctuation. And here we apply absolutely no filtering, no shape removal. We simply work out straight from the measurements. And what we can see is, of course, the SA varies, but it varies only by a factor of 3, while kurtosis and skewness will vary by a factor of 4 and 6. What is interesting as well is the kurtosis will immediately tell you whether you have burrs, and those burrs will prevent the proper contact between, mechanical contact between ultrasound sensor and the bottom of the cap. So whenever you have a flat surface and any defects of burrs, the kurtosis will spot that out while the SA won't. The skewness again will show how flat the surface basically is, and getting something as close as to 0 is perfect. And in that case, if there's any skew like here, it will be shown. But again, if you have something flat with some spike, you may not see this in skewness. So both parameters in that case were implemented in order to provide an entry control of the cap before to assemble the sensors. To continue with mechanical properties, we can use roughness and correlate this roughness versus the wear and tell when it's time to, let's say, replace a part. The example shown here is about the cylinder inside the engine block. So we use a special objective that deflect lights in horizontal ways, such as the wall, the roughness of wall can be measured. So out from manufacturing, a cylinder is nicely textured with awning and has a certain roughness, and the one which has been used quite a lot shows this different height profile. So what we can see here is we will use actually the bearing curve, or so-called Firestone graph or Abbott curve, where we plot the probability for a point to be a certain height. So here you start always from the left with where the peaks are, and at the bottom this is where the valleys is. And from that curve you can actually work out different parameters, which are the volume of peaks, so the VMP, or the volume, core volume on the top surface, as well as what we call the lubricant reservoir volume with the VVV. So these V parameters are part of the new areal norms, and they can help you to directly quantify how performant and how much wear you have. So the idea for a bore cylinder is to have a certain number of grooves to help and have enough reservoir for oil, such as there is a lubrication between the pistons and the cylinders that travels inside. So in that case, having this awning helps you to get the reservoir, and you see that whenever it wears out, this reservoir disappear. So we are in a condition of starving lubrication regime. So we will certainly go to engine failures. Also, even so, we are not valuing a lot of peaks. At some point we want the piston to nicely slide across, so we want to minimize the contact area between this piston and the wall cylinders, and in that case if we start and see that this VMP start to decrease a lot, we know the contact area will increase, and then there is a risk of adhesive behavior with the piston. So basically we are just stopping the piston from the travel. So in that case, it's easy to see and quantify the evolution of VMP or VVV to understand whether the engine will run well or whether there is some change. Also, there are elements where we can look for aesthetics. So in that case, we have the metal belt ring where we have glossy and shiny surfaces, and most of the very high-end brands like to get a certain aspect of gloss, and we can still measure the surface with gloss meter, but usually people assess the gloss by eye, and it doesn't tell you what kind of change you need to do on your process whenever you have a good or bad gloss. Here's the two images for good and bad gloss. And what you see is it's less than a square millimeters, so we use a 20x objective, such as we have enough lateral resolution to capture the element that plays a role into the gloss. In that case, it's quite challenging to see and tell the difference by eye, but actually we look for the average roughness, average slope fluctuation, called SDQ as a parameters. And what you see here is 6 measurements on a nice gloss surface and 6 other measurements in a not enough shiny surface. And in that case, you clearly see that you have a certain slope fluctuation in degrees, and on the other part the level is below. So you have almost a 0.5 degree difference, which is pretty small, but it helps you to understand what you need to do. So here, to get the right shininess, you actually need to roughen a bit the surface. So this process is pretty fine. Also, SDQ will be challenging in terms of vertical noise. So any vertical noise will kill out the signals, and you won't get such a nice clear differentiations. Also, lateral resolution plays a role here. If we use too low magnification or not resolve enough technique, you won't see the pattern which is responsible for the gloss. SDQ can also be in use for mechanics like brakes. So whenever you brake, you want it to be nice and quiet instead of noisy, because you have, in case of noise, you have like a feeling of being unsafe. Here you see the two surfaces were of brake pad were in spec, and the braking disc was okay in terms of mean roughness. However, it was not okay in terms of making noise. And actually, the main reason is simply what you want is a certain grip and a certain spacing between these peaks. In that case, the frequency plays a role. So SDQ again is into scope by measuring directly the slope. So SDQ itself can replace this parameters, can replace SA as a parameters, and getting two key informations into one single parameters. The last one is really about predictive maintenance for rotating shaft. So whenever you have a sealing and rotating shaft, again, we want a proper sliding conditions for this elastomeric lips, and we don't want any leak of oil. So in that case, we use parameters based on peaks to determine the density of peaks, as well as the invert radius of this peak. So for best sliding conditions, we want a certain texture, so we want the radius to be short. We want them to be short as well, because if it's too large, then you start to create a leaking path for the oil. So if you have a small radius, for instance, the pressure and the deformability of this elastomeric seal will fill in the gap and avoid all oil to escape. So in that conditions, you directly quantify and specify exactly how the surface of the shaft should look like, and make sure that you don't rely only on SA that gives to you no clue whether the surface will leak or whether your lips will be burned because you have too high adhesion between lips and a flat surface, for instance. The last example is about additive manufacturing. So here we have an example where we have 3D printing of polymers through a hot nozzle, and this nozzle will build up the parts step by step. So if you look to the side, what you will see is a regular spacing of lines. However, 3D printing, especially for peak materials, is pretty challenging. So you really need to fine-tune the process in terms of printing speed, temperature of the nozzle, such as you have a nice sticking between the layers. Otherwise, you create cracks and your part falls into pieces. So in that case, you are interested to have a very joined, a nice connection between every layers. So this is what we call here a good process. Whenever you start to have too high speed or too high temperatures or the wrong printing parameter in general, you start to create some subduction between lines, and you have no more straight line but really spurious and fluctuating lines. In that case, if you look to the roughness, basically you get rough and rough surfaces equally. So the best is to filter out a bit of the waviness in order to only extract this line spacing, and work about for the autocorrelation length that tells what is the spacing at which the surface repeats itself. This is a perfect example here. You see a 77 spacing, while here you get 88 spacing, micron spacing, because you start to get the fuse and the system start to not look for one but several of those lines together. So plotting the autocorrelation length parameters versus their experimental conditions will help you to converge toward best conditions, and you also have an control as a output quality control. You will get and use these parameters. So as you will see, as you saw, basically the areal roughness parameters has been very well designed to link their parameters toward the functions, and I've listed multiple functions here, and everything is green shows strong correlations. Everything which is in red show no correlation. As you can see, there's a vast majority of green colors, and I said it all depends on how good the roughness measurements is made, as well as which cutoff you extract to get these correlations. So that as a conclusions, it's clear that getting a full area measure through a non-contact profilometry technique really allows to capture complex textures and make sure we extract some valid parameters out from a surface, and having on top the proper transfer function that will help us to have a high lateral resolution, almost sub nanometer vertical resolution, helps us to plot all the components on the surface and be in a position to select on a given case the right component that plays a role. And this is very critical then to have a technique that allows a large field of view to make it redundant and make it statistically representative of the surface. So in short, you will have then three main techniques to measure surfaces, which could be a stylus for quick long trace and reliably measure a roughness on thin transparent layers. You will have focus variation for everything which is textures or steady slopes. This will be the technique of choice. And for the rest, where you will need large field of view and some microns roughness assessment, white line interferometry will play a role. So thanks for your attention, and now it's time for getting questions. It all depends on applications, and this is what I call the component of the surface. So for instance, when we started all those case studies, we didn't know in advance what kind of role the different components were playing. So we were ending up by refining, let's say, roughness, or let's say some macrons roughness or micro roughness, which is more in orders of tens or hundreds of nanometers. And in that case, white line interferometry was the key technique to use. But if you end up with having and identifying that this is the waviness of 10 microns amplitude, then focus variation will certainly plays a role. And vice versa is also in terms of refining the smallest or the details that plays a role. So in terms of the metallic belt, for instance, it was clear that we needed to go from the standard 5x objective we use for all other study to a 20x objective to gain lateral resolution and to properly see those details that actually play the role into the shininess. So it's really a trial and errors and refining then the scale, lateral scale and vertical scale in which we get the data, relevant data, and then we can adjust the technique accordingly. So usually adhesions, like it can be adhesion of paint, adhesion of polymeric films. Usually those parameters are nicely described either by the V parameters. So if you have a certain volume of void, then the polymer and the painting can just anchor to that surface. There are cases where a simple average mean slope will do the job, because basically what we want as a surface to anchor with polymer or painting, you want something to anchor, but you don't want too sharp edges that will create a stress point. So the SDQ will be also a way. The last one will be the SSC and SDS, which are the density of the peak, as well as radius of curvature of this peak. So in that case, the adhesions was between ink and the surface.
Thanks, Samuel. So the next question is regarding the slide 25. So how do we compare before and after surfaces for volumetric parameters? In my experience, the mean plane to obtain these cannot be manually changed in Alicona or even Bruker Profilometer. Its application is sheet metal forming.
So right now, at least in terms of modern Vision 64 software, and since the version 5.6.60, we have ability to recess and get the zero plane adjusted in a proper way. And usually we adjust it either to the mean plane, either to the top surface in order to compare different surfaces. There are also elements with vision map from the OEM, from Digital Surf we have integrated that could help to really get the leveling properly and make sure we reference the wall bearing curve in appropriate manner. So the short answer, at least for white line interferometer, the latest versions of software allows you to really offset the curve as you want. And for Bruker Alicona, you can still have the choice to go through mountain software, for instance, to adjust that. And I think, as far as I remember, the software as well will allow that in coming version. So now we have another question. Which is about the contact profile of deck tag with a 2 microns radius. Basing on the measurement parameters, the lateral resolutions reported shows 0.0003 microns, 3 nanometer. Is that realistic? So it's a good question, and this is the pitfall I was mentioning on the slide. Here, the 3 nanometer lateral resolution is actually the spacing between two adjacent digitalized data. It does not represent reality, which is a 2 micron status will not see below than 1 micron details. And it's like sometimes it's more complex because the flatter the surface is, the better we can sometimes resolve some details due to the vertical resolution. But in the first sense, 2 micron status means you are filtering everything below 2 microns, basically, irrespectively on how much data point you can digitalize afterward. So this is the typical pitfall here. There's another question regarding the value of VPN can be used as a number of quantifying asperities on a surface. So in terms of numbers of asperities, the V parameters all brings some kind of square, let's say cubic micrometers per square micrometers. So it's just more a statistical view, and it does not tell you how much asperities or pores you have. For that, you better need a proper segmentation of the surface and break down to numbers of pores and calculate the volume of this every single pores. On our software, we have this ability to segment the surface and extract numbers of pores, volume, area, projected area. So in that case, it will be more suited in that case. So in your first slide, you talk about lateral resolution, objective 2.5x, optical resolution can change from 3.8 to 2 microns. So again, what we see here is the difference between the true resolution from objective versus the digitalizations on the camera sensor. So the 2 microns means we have an oversampling of the true optical signals, which is 3.8 micron. So it will help us really to see up to the limit of the objective. So that's the same answer as the stylus. Another question was, why example of correlation were given with white line interferometry? Can focus variation also provide correlation between roughness and functionality? Yeah, the answer is definitely yes. They showed a very nice correlations regarding the cutting tools, especially with all the bearing functions and analysis of the roughness on this tooling. So, and as I said, depending on application, you may not require high lateral and high vertical resolutions. You just need to be appropriate and adequate with what you want and measure, and which component of the surface you want to measure. Is there any specific question why coherent scanning interferometry is better suited for roughness and functionality match? Well, definitely white line interferometry or coherent scanning interferometry is really best suited for sub-microns roughness. So with such a lateral resolution and such a high vertical sensitivity, we can definitely get the best match with any kind of functionalities. But that being said, if the surface become way rougher, like for the raw additive manufactured surfaces, for instance, the wall focus variation technique will be more suited and easier to use. So it depends on really applications. And how many examples shown are compliant with the areal roughness norm 2578? Well, all examples shown are compliant, simply because we should have stated further the cutoff, objective use. In that case, it would have been fully compliant. But as the norm for areal roughness tells, we can manipulate the data as we want. So we can remove a form and shape and do whatever calculation we want next to it. So it's much easier, and then it's always compliant with 2578. Well, I've ended now with all the questions regarding at least listed. Thanks for your attentions. It was my pleasure to present this webinar. If you have further questions, you can reach me out at samuel.lesko@bruker.com. Thanks and goodbye.